involved in this section, I kind of just want to like recap everything, because it feels like we've done a lot, but I feel like it hasn't been hard. It's been like computational stuff, right? But it's just like maybe a matter of remembering everything we've done. We've been working with vectors, which is something that has a magnitude, which is basically the length, and a direction, right, an arrow which way, and some angle with an axis or something, right? And what we've loved to do is we had component parts where we said, okay, if you split it up into its x and y, then you could say, whatever the length is in x, then whatever the length is in y, right? Oh, and that was super nice for us because doing that makes right triangles. And when there's right triangles, we can do trig to find sides, aka the components, right? X and Y. Or we can find the magnitude, right? Pythagorean theorem, right? Right triangles are always nice, and it's a good thing because you can almost make them exist anywhere. And that's really what it boils down to. And then on top of that, we did addition and subtraction, which I think we're okay with. And then we did the dot product, if we had this times another vector. Remember, the dot product spits out not another vector, but a number. That'd be 3 times 4 plus 5 times 6, right? You do multiply the components, but you add them together. And then there was the cross product, right? And then we could also multiply by a scalar, right? If I said 3 times that, then you would just do 9, 15, just, right? And then there was the cross product where if we did like 3, 5, usually we did it with 3-dimensional ones because it doesn't really, not dot, cross, right? I don't know. And if we did that, I'm not going to go through and do this, but then we had the determinant I, J, K, and then 3, 5, 2, -2, 6, -4. Then you do I times, if you cross out these, the determinant of those. That might take a little bit of review if we ever need to run into it. But that's essentially the rundown that we've done, right? We have vectors, magnitude and direction. They have component parts, x and y. We can make nice triangles out of them. We can add them. We can multiply by a scalar. We can do a dot product, cross product. That's basically all we've done. Now we're going to apply some of that knowledge. This think/warm up might be a little, I should get you guys a little participation sheet. I always kind of forget about it. That think/warm up might be a little weird because you guys are, it's always hard asking not a specific question. But can you think of any general strategies to use or things to look for when solving problems involving vectors? Just in general. What's something super useful that you like to do? Anything? Yeah. What do you mean by that? That's great. That's a great, yeah. Simplify everything as much as you can. Multiply it out. Get it in terms of one vector. If you're adding vectors, right, obviously, it's only in one. Yeah. Smaller chunks. Yeah. And I think the one that I am really thinking of that you guys probably are already thinking that it's automatically in, I think the biggest help in like 95% of the problems is breaking it up into components or making it components, right? If it says like you're at point A, which is 2, 5, and then you go to B, which is -3, 2, right? Make that a vector in components, right? From A to that's -5, and then the Y is the change of -3, so that's the actual vector is -5, -3, X and Y, right? Because then also when you, is that confusing? We figured about it. So like if we had A, which is at 2, 5, somewhere there, and then we go to B, like if we have the vector AB, B is at -3, 2. Then we've gone -5 to the left and -3 down. And what's nice about breaking it into components and stuff is, what do you get here? Oh, right triangles. Who loves right triangles? Let me ask again, that was pathetic. Who likes right triangles? Everyone's hand better be up. Right triangles are amazing. Anya's still a little, she's like, maybe, I don't know. Isosceles triangles are nice too. Scalene they're fun. Right, Anya, that's what you were thinking? Yeah. Okay, we're just going to go through one example today. I should talk about this first, I guess. Vectors can be used to represent any quantity that has a magnitude and direction. Common examples include force, velocity, weight, and gravity. Physicists often use vectors to represent these quantities. We all love physicists. They do a great job. Physicists have a lot of jobs in the world. All right, we've kind of done one like this before, so this would be a good intro one, a good Monday one. Easing us in. 2 rodeo clowns are restraining a bull. This is kind of like that wheeling a lady in the stretcher, like who's measuring the force on this bull that 2 people are like restraining? Who cares? But the whole point is like yes, you won't be doing this for a bull, but think of any time a force is put on something ever, or multiple forces are acting on something ever, and you can calculate it. That's pretty important. I don't know. Car crashes. Yeah, life is in direction, isn't it? Or in 2D. Suppose one clown is exerting a force of 270 newtons due north. Well, once you think 270 newtons isn't a lot. Yeah, but the bull, you have to think the bull's pulling up. Yeah, but so yes, he's stronger than the bull. Yeah, I'm pretty sure a bull pulls way more. Maybe, I don't know, yeah. This is after I think they're falling off. Like now they're trying to get it back in the. I think the bull still would be pretty strong. Yeah. I'm kind of like, I never understood people that do that. Like that's terrifying. How could you get like? People have had to have died doing that, right? The bull stuff. Okay, that's. I don't even want to. Ugh. Yeah, every time I see someone get like, I'm like, how is that horn not just like going through them? Most of the time they're just gonna, I don't know. Ugh, God. Anyway, suppose one clown is exerting a force of 270 newtons due north while not getting stabbed by bull's horns, and the other one is pulling a force of 360 newtons due east. Draw a picture. Even if it doesn't tell you to draw a picture, with like all the problems in this section, and whenever you're presented with a real life problem, I'd draw a picture, right? So we have 270 newtons north. North is up. Newtons. And 360 east. That's about it. Determine the resultant force and the angle it makes with the east-west axis. Well, hey, wasn't resultant just what ends up if you put these two together? So I don't know, maybe I like to think of everything on an axis. We can go 270 up, right? And then if we tip-to-tailed it, we can go 360 there, and then the resulting vector would be this. This guy, maybe I'll do it in a different color. Right? You put these two together, and you get this guy. Right? Add that one and that one, you get that guy. Should there be like a thing on the top? I'm not a good artist. I'm just going to leave it like that and let your imagination go wild. I'm a party at.
To the right, it looks like the little screen that you normally have.
Oh yeah. Oh yeah. Okay. Well, how do I find the magnitude? Magnitude is the length of that. How do I find the magnitude? Yeah, I could use that Pythagorean theorem. So a squared plus b squared equals c squared. We got a right angle there because we broke it up into its components basically. And also, you know what? I'm also gonna maybe write it this way too, right? Because you could do it both ways. You could add that one first. Maybe just because that triangle might look better, the bottom one. Well, the two legs, 360 squared plus 270 squared equals c squared. Square root both sides. We don't need a plus or minus because we can't have a negative length or magnitude, right? So we're running at c equals, just throw. Okay, I trust it. 450 what? Newtons. Sure.
Well, isn't it?
That's a great question. I would assume probably because of the whole conservation of mass and energy and everything. I would assume it's labeled after him. Newtons are technically newtons are kilogram. Newtons, the actual unit of newtons is kilograms meters per second squared. It's weird. F equals ma, mass times acceleration, meters per second squared. It's a little, kind of a hard unit to imagine, I guess. Okay. Well, it also wants the, what else does it want? It wants the direction, the angle. How can I get the angle? How can I get this guy here? Yeah. Technically, you can use any one of them you want because we just found that this is 450, right? But yeah, if we're working with our original ones, then the tangent of theta equals, and I'm going to leave some space on purpose because I've been in pre-calc and we all did chapter 5 and we know what's coming, maybe. Opposite 270 over adjacent. Once you see why, you'll be like, oh. Now, what do I need to do to find theta?
Oh, yeah.
Tan inverse, which is why I left this space. Tan inverse, right? Oh, remember back in chapter 5 where I was like, hey, if you're looking for an angle, you better be taking the inverse. Right, so then theta equals, what are you getting? 36 points. Yeah. And then if we wanted to be a little bit fancy, to be specific, since it gave us the problem in terms of north and east, right, not on a coordinate plane, we could say north of east